Hello there. My name is Will Grothwall, and I'm going to talk to you about my paper, Oops, I Took a Gradient Scalable Sampling for Discrete Distributions. This is joint work with Kevin Swirsky, Malad Hashemi, David Duvino, and Chris Madison from the University of Toronto, the Vector Institute, and Google Brain. So in this work, we are mainly concerned with energy-based models. And an energy-based model is a way to parameterize a probability distribution, which takes the following form here as the exponential of this function, which we call the energy function, divided by the distribution's normalizing constant. And we can see here that the normalizing constant can be implicitly derived from the energy function. So this function is all we need to fully specify our model. And it's further worth noting that the energy function can really be any function which maps from the data to a single scalar value. And so this gives us tremendous flexibility for how we want to define our model, and gives us tremendous ease to bake in whatever structures or invariances we would like into this model. To train energy-based models, we would optimally like to maximize likelihood. But as you can see here, computing the likelihood involves computing the normalizing constant, which is in general intractable. Thankfully, the gradient of the log likelihood can be written with a much more convenient expression, as you see here. This expression involves an expectation over the model distribution. So if we can draw samples from our model, then we can estimate the log probability gradient, which we can use for training. Of course, sampling from unnormalized models like this is not easy, so we have to resort to sampling techniques like MCMC. In the past few years, there's been tremendous success applying energy-based models to large-scale probabilistic modeling. Most of these successful methods parameterize the energy function using a flexible deep neural network. So now the question is, how do we draw the samples that we need for training? Well, if our data is continuous, then we can use gradient-based sampling methods like Langevin dynamics, Hamiltonian Monte Carlo, or Stein variational gradient descent. And it's this combination of deep neural network energy functions and gradient-based sampling that has given us very high quality results in image generation, semi-supervised learning, out-of-distribution detection, adversarial robustness, and many other applications. But what do we do if our data is discrete? Unfortunately, there are not nearly as many scalable and successful sampling approaches for drawing samples from discrete distributions like this. And this is especially problematic because many important and interesting types of data are discrete. Things like text, tabular data, protein sequences, molecular graphs, all of these data types are discrete. And if we want energy-based models to be a generic and useful tool for probabilistic modeling, we need some pathway forward to apply them to discrete data. And so in this work, we choose to focus on sampling of discrete distributions to enable EBMs to be applied to this type of data. We present a new sampler for discrete distributions. It is a very simple approach which exploits a shockingly common structure in many discrete distributions. Our new sampler increases efficiency, enables deep energy-based models to be applied to discrete data, and improves the training of many classical energy-based models. So, like I said, we focus on discrete sampling or drawing samples from distributions of the following form where the normalizing constant is not known. And we restrict our study to d-dimensional binary or categorical variables. Perhaps the simplest way to draw samples from distributions like this is known as Gibbs sampling. And this works by picking a dimension I and then resampling the value at that dimension while holding all of the other dimensions fixed. So to do this, we first pick a dimension, and then we evaluate our distribution's log likelihood function at our current sample. We then flip the value at that dimension and then reevaluate the log likelihood at this new flipped example. Then we will update our sample to this new value with a probability that depends on the log likelihood difference between our initial sample and our new proposed sample. Now, to ensure that we thoroughly explore the state space, we must do this to all of the dimensions in the input. And the way this is typically done is we fix an ordering over the dimensions and then repeatedly iterate through that ordering. And this is known as raster scan Gibbs sampling. But as we'll soon see, some dimensions actually might be better to flip than others. So imagine we have a model of the MNIST data set, and we pick this pixel here to flip. It's currently black and it's in the background. And we can imagine the likelihood of having this pixel white is going to be much lower than the likelihood of this pixel being black. So what that means is that if we propose to change it, it's not going to change. And that means that we've not updated our sample, and we've effectively wasted all of the computation that we used to potentially change it. Similarly, if we choose this pixel, it's on the interior of the digit and it's currently white. The log likelihood of it being black is going to be considerably lower than its current value, meaning it's not going to change, and again, we've wasted all of our computation. Realistically, the pixels that are likely to change are the pixels on the edge of the digit, because we know MNIST digits can be thin or fat. But actually, this is a very small subset of all of the dimensions in the input. And in some of our experiments, applying raster scan give sampling to MNIST models leads to only 2% of the pixels actually changing. And this means we've effectively wasted 98% of our computation. But further still, we can see that the pixels that are more likely to change actually depend on the entire input. We can see here the pixels on the edge of this 4 are very different than the pixels on the edge of this 1. So perhaps a more efficient avenue for sampling would be to choose dimensions which we think are more likely to be accepted. So what we can do is we can place some proposal distribution over dimensions, which is conditioned on the entire input. And then to generate a proposed update, we sample from our dimension proposal and then flip the value at that dimension that we sampled. And then we can accept or reject this sample using the standard Metropolis-Hastings acceptance probability, as you see here. So now the next question is, how do we design this dimension-wise proposal? Now, since every example that we propose is going to be different than our current example, really, we just want to maximize the probability that these new changed proposals are accepted. And we can see here that the Metropolis-Hastings acceptance probability has a few terms which we would want to maximize separately. The first term here is going to encourage us to propose new samples that have very high likelihood. But this second term here is going to encourage our dimension-wise proposal distribution to have very high entropy. And these two terms are somewhat at odds with one another, so we need to find a way to balance them for efficient sampling. So one potential idea for this would be to make our dimension-wise proposal distribution proportional to the log likelihood difference between our current sample and flipping each bit. And so really this is a tempered softmax over all of the dimensions, where the log probability is given by that probability difference of flipping each dimension. And now we have this one parameter, which is the temperature of this distribution. Now we can see by plugging this form of the proposal into the Metropolis-Hastings acceptance probability that if we set this temperature to 2, then the most variable terms cancel out, and we're left with a much more simplified expression, which is just the ratio of the normalizing constants of the proposal distribution going forward and backward from our proposed point. And we can see that if our distribution's log likelihood function is well behaved or has a reasonable Lipschitz constant, then this ratio is going to be very close to 1, which means that we're going to almost certainly accept the samples that we propose. And it's actually been shown in some prior, more theoretical work to our own that proposals of this form are actually near optimal over all proposals which make local moves in discrete spaces. So now the next question is how do we compute this type of distribution? We can see here that we'd like to sample from this proposal, but to compute this and sample from this distribution, we'd need to compute the log likelihood difference of flipping every single bit from our current example. And to compute that, we would need to make O of D function evaluations, where D is the dimensionality of our input. And so if our log likelihood function is slow to evaluate, or our dimensionality is large, this can lead to very inefficient sampling. So with that in mind, let's look at a fairly broad family of discrete distributions. We have some simple distributions, some classical energy-based models, some latent variable models, and deep energy-based models. Now, all of these are very different in the types of structures they have, the problems that we would apply them to, their general complexity, but there's one thing that binds them all together, and that's the log likelihood functions here can all be written down as continuous differentiable functions which accept real valued inputs. And the discrete structure in the distribution is created, in a sense, when we restrict our inputs to be a discrete subset of their possible values. So consider the Ising model here in particular. This function can be evaluated when x is any real value, but it only becomes an Ising model when we restrict x to be -1 or 1. And so we can exploit the functional form of these distributions and their gradients to estimate the quantities that we need for our proposal distribution. In particular, we use a very simple first-order Taylor series approximation to estimate these values. And further still, we can actually come up with a very efficient expression for evaluating the log likelihood differences of flipping every single bit in our input. And we can do this using only one call to the gradient of our model's log likelihood function. The expression for binary data is written there, and a similar expression that's just as efficient for categorical data can also be derived. So now this leads to our approach. We propose a new sampler for discrete distributions. It's a Metropolis Hastings sampler with a proposal that approximates this proposal distribution here. We approximate it using a very fast Taylor series, which enables us to sample from a very similar distribution using only O of 1 function evaluations. This is a very simple, very efficient MCMC sampler that has no hyperparameters. And because of its relationship with Gibbs sampling, we call this approach Gibbs with gradients. So seeing our approach visually, we are trying to sample from this discrete target distribution. And this distribution, like many realistic and important discrete distributions, it is actually defined by some underlying continuous function. So we use this underlying continuous function and its gradients to make predictions about the likelihood in nearby discrete states. Then we use these predictions to parameterize a proposal distribution over discrete moves. We sample from this proposal and apply a Metropolis Hastings correction to update our sampler. We can see the pseudocode here is very simple, and it is just as easy to implement Gibbs with gradients within standard machine learning frameworks like PyTorch, TensorFlow, and JAX. So now we get to some experiments comparing Gibbs with gradients with other samplers. First, we show visually drawing samples from a pre-trained RBM on the MNIST dataset. We can see here that Gibbs with gradients draws samples that are realistic and notably much more efficiently than Gibbs sampling does. Next, we look at image denoising using Ising models, which is a conditional sampling problem. As you can see here, Gibbs with gradients arrives at a reasonable solution much more quickly than Gibbs sampling. And in this example, we've actually overlaid the dimension-wise proposal distribution on top of the Gibbs with gradients images, and in red. And you can see here that the proposal focuses on aberrant regions and also regions near color boundaries, as we would expect. Next, we're going to look into training energy-based models on discrete data. So as I mentioned earlier in the talk, we can estimate the gradient of the log probability of an energy-based model using MCMC sampling. So MCMC sampling can enable us to train these models with gradient-based optimization. So now let's look at two applications of training EBMs. First, we're going to look at protein contact prediction with POTS models, and then next we're going to look at deep energy-based models for image data. And so the task of protein contact prediction is very important in computational biology. So we are given a protein sequence, which is going to be a d-length variable, and each of the variables is going to take on one of 20 possible categorical values. And we're interested in knowing which pairs of these variables are going to be in contact when the protein folds. And so traditionally in the computational biology community, this is solved by training an energy-based model known as a POTS model. And then we can actually train this model and inspect one of its parameters, which is called J, which infers pairwise interactions between the amino acids. And then we can look at this inferred parameter and then take these smaller values and make predictions that there will be no contact, and look at the larger values and make predictions that there will be a contact. And we compare various approaches for training the POTS model on protein data. We compare pseudo-likelihood maximization, which is kind of the standard practice in the field, with two approaches to maximum likelihood based on Gibbs sampling and our sampler, Gibbs with gradients. We train POTS models on protein data from two very large proteins, which is considerably larger than you would normally see this method applied to. We see on our smaller protein that both maximum likelihood approaches notably outperform pseudo-likelihood. But on our much larger protein, maximum likelihood with Gibbs degrades in performance considerably below pseudo-likelihood, while at the same time, Gibbs with gradients retains its high performance, outperforming Gibbs and pseudo-likelihood maximization by a large margin. So next we look into deep energy-based models for discrete data. So as I mentioned, Much of the recent success in energy-based models parameterizes the energy function with a flexible deep neural network. And this approach has never really been shown to work before on discrete data. So here we train energy-based models parameterized by deep residual networks on binary and categorical image data. Here, the binary values are treated as 0 or 1, and the categorical values are treated as a 1 of 256-way categorical. Now, this means to apply Gibbs sampling to this, just to do one step of sampling, we would need to evaluate our energy function 256 times. Comparably, Gibbs with gradients requires only 2 function evaluations, and it converges in considerably fewer evaluations, meaning that it's going to be much, much more efficient for these kinds of distributions. We train these models using persistent contrastive divergence, which is the state of the field for continuous energy-based models. And we find that our ResNet energy-based models trained with Gibbs with gradients outperform variational autoencoders and more classical energy-based models like restricted Boltzmann machines or deep belief networks. And our models trained with Gibbs with gradients notably outperform the same models trained with Gibbs sampling. Here we can see some samples from our models generated by a very long-run annealed MCMC chain. So I would refer you to our paper for additional results on energy-based models of text data, structure inference in Ising models, and many additional sampling experiments. So once again, I'll just want to say thank you to my co-authors, Kevin, Malad, Dave, and Chris. Our code is available at the link you see there. You can find me on Twitter at wgrothwall or at my email, as you see there. And I really hope that everybody comes to the poster session. Thank you so much.
Good. We have some time now for questions. I was looking at the Rocket chat. I think there are no questions there, but I have a few questions. I think it's going to be Will who is going to answer these questions. So,
yes.
Good. So my first question is obviously one of the best methods for sampling with continuous variables is Hamilton Monte Carlo, and my question is about any potential connections of this technique that you described with HMC or so. HMC is also well known for making use of gradients, and here you are using also this, but for dealing with discrete variables. HMC also uses auxiliary variables. Is there any potential way of using maybe similar techniques in this case with discrete variables?
I think that's a really interesting question, and actually, me and Chris spent some time after we developed this trying to incorporate momentum variables like you would see in Hamiltonian Monte Carlo, but we found it's considerably more challenging to incorporate to come up with like an energy conserving Hamiltonian in discrete sampling. I think there's a lot of promise incorporating some like newer ideas in like non-reversible MCMC techniques to sort of get around that. But at the moment, we have not figured that out yet. But I think that's a very interesting direction for this to go in the future, certainly.
Good, thanks. I'm looking at the chat and we don't have any questions there. But I can ask another one. Okay. So obviously, this is really good for sampling from these discrete distributions. Another challenging problem is optimization with discrete variables. And my question is, do you see any potential connections there for using this type of techniques for optimization? Could be of any use?
Yeah, I mean, I think this could be like certainly plugged into a sort of a simulated annealing type of algorithm. Actually, me and Kevin have done some experiments on trying to use this use Gibbs with gradient sampling to solve like SAT problems, because you can encode those into Ising models. And so I think that is definitely something that could be done, and we've had some success with it on the specific SAT problem. I think the difficulty comes in the fact that I guess this, the method is sort of in more of like the local search domain where we are making smaller updates. And I think getting around that would require us to go to work on maybe with to incorporate things like parallel tempering, or to incorporate larger window sizes or larger Hamming windows into our proposal distribution. And that becomes a little bit more challenging because the size of that, grows exponentially. But I also believe that there are potentially some maybe like dynamic programming tricks we could use to sample from those larger proposals. But
Good.
I do think that, yes, it's an interesting direction.
Thanks a lot. We are running out of time, but yeah, thanks a lot for your answers. We are going to move now to the second part of the session. We'll have now a series of short talks. There are about 6 of them. We'll have then after this some time for questions at the end. So please, just as you watch the videos for the talks, write any questions that you may want for the authors in the Rocket chat. Thanks, and let's move on now to the short talks.